Morning. So I'm Morten Rasmussen. I work for ARM. I've been around for a while. I think I've been at all the OSPM summits in the past. And I have the pleasure of bringing up the first topic this time around. I haven't prepared a lot of slides, so I hope you're all awake and ready to engage in an interesting discussion. So I've looked at a lot of things in scheduling over the years, and we've done some recent work in some of the hardware that we have coming up, where we have some problems related to scheduling. But I'm going to involve a few more things into the discussion just to provoke a few people. I think I presented at LPC some years back that there are some problems with energy-aware scheduling and our abstraction in terms of how fast the CPU is on asymmetric systems. That we have this compute capacity, which is a kind of very simplistic view of viewing what is the throughput of a CPU, because microarchitectures are different, which means that depending on what workload you're running, your throughput may or may not be very suitable for a microarchitecture. So on big little systems, you can see that for certain workloads, the difference between big and little is huge, and for others, it's not so big. And for energy efficiency, it's kind of the same dynamic. And that led me to bring up the topic if our current abstraction is actually sufficient for what we want to achieve. And I think there is a bunch of things that have been going on over a few years that kind of suggest that maybe our current abstraction isn't quite sufficient for what's needed for real products. So I've tried to pull in 4 things that I could think of that kind of points in that direction, just to provoke some discussion. So there is the energy model abstraction. There is the observation that at least in the Android ecosystem, it seems that most products are shipping with heavily modified schedulers. So that kind of points in the same direction that maybe our abstraction isn't quite good enough. Then there are some hardware aspects that kind of breaks some of the assumptions we make in EAS. There are all sorts of dependencies which are often very platform specific, and they're often different from generation to generation, which makes it really hard to come up with a generic abstraction that will just work for everybody and is kind of future-proof. And then last, what I've been looking at recently with one of my colleagues who's here as well, where's Christian? He's there. Related to some new architectures challenges where we have shared compute units between different kinds of CPUs, and therefore we want to bias scheduling for some things. So I'm going to go through those in a bit more detail, and then what I really want to arrive at is a discussion about is our EAS abstraction the right one? Should we extend it in some way? Should we allow the architecture to override more scheduler decisions? Should we actually go in and define some more architecture callbacks? We have a few today, but should we go further than that? So this is actually a slide that I showed at LPC in 2022. So here we profiled 4 different workloads on a Pixel 6. And we measured the power and normalized performance, so each color is each of the 3 types of cores we have on that phone. And the curves are basically the frequencies. And it might be a little bit tricky to see, but I've tried to sort of highlight it with the lines here that the peak power you're seeing varies quite a bit. The relative performance also varies quite a bit. You can see that the red curve, which is the mid CPU, it ends less than halfway up the big curve. So it means that on this particular workload, peak performance on the medium core is less than half of a big core. And on the next one, it's way better. So it means that if you have some of those workloads that can be accommodated on both types of cores, you can make some wrong decisions here if you kind of decide that I'm just going to assume that my medium core is always topping out at 60% of the big core, because that will not be true for all workloads. What's on? Yeah.
Have you been able to compare if their compute capacity, they are all almost the same, or you can see that for the fourth use case, in fact, the big core is only half the compute capacity compared to the first use case? I mean, have you tried to estimate that everything is 1024 and that's it? Or?
So this is normalized, so the big core is always the highest performance, because how do you define throughput of a CPU? Because it's really about the relative performance, isn't it, between the two cores. If it drifts relative to each other, then when you sit on a big core and look at the capacity of a medium core and assume, okay, if I assume that the mid core is always 60% of a big core, and I'm on a big core, and I can see my utilization is 50%, well, then I should be able to accommodate on the medium core. But then if you're on this workload, and you stick it there, then you realize, oops, actually I do not have the throughput of that core that I thought, and then your user experience suffers, and you might end up at a different point in your DVFS curve than you thought, which means that the estimate you made using EAS was wrong. So you might end up actually burning more power because you need to drive it harder than you thought.
I was wondering, for example, if that could be doable to have something like CPU intensive workload on big core is 1024,
yep.
But then memory bounded on the big core is only 512, for example, because we know that we can't run that much instruction per cycle, which means that you still have one, and you can also accommodate everything.
You can, of course, change how you normalize the performance. You just need to define what does capacity mean. I think what I'm getting at here is that capacity is just a one-dimensional thing. It's actually multi-dimensional.
Something like the number of instructions per second that you can do according to the use case, and we know that depending on which instruction you're running, you will not have the same instruction per cycle. And then based on...
Yes. The thing with IPC is that it's kind of nice to observe how high your IPC is, but reasoning about why you have the IPC you have is incredibly hard. You actually need more fine-grained detail. You don't know if a low IPC is because the workload doesn't fit your microarchitecture, or if it's for some other reason. It could also be that it's just super memory intensive. So you kind of need that knowledge on top to figure out what's going on. Daniel?
What kind of workloads are you running?
These are actually 4 of the sub-benchmarks of Geekbench 6, which is a very commonly used workload, especially in mobile. So even across standard benchmarks, you see quite a lot of variation. I don't remember which one is which anymore. But they do exhibit different behaviors. So you would find, for example, something which is very branchy, where the branch predictor is often wrong. That generally fares better on a medium core relative to a big core than the other ones. And you can kind of imagine that if you have a very long top-tuned pipeline, if you consistently get your branches wrong, then you're losing a lot. Where if your pipeline is a little bit shorter and mispredicted branches will have a smaller performance penalty. And also efficiency. That's actually one of the things we're looking at. That is how often is speculation wrong, and some of the least efficient Geekbench 6 benchmarks, that's because the big cores, there's a lot of speculation that turns out to be wrong, and that's just wasted power. Right. Yeah?
Ricardo had his classification stuff at some point.
Yeah.
And we could use a scheme like that to add a dimension to his scaling.
So it doesn't do what we really expect, because it is calibrated with some specific workloads, not with
our classification stuff. It doesn't. Maybe.
No, it's not. You need to calibrate to actually get anything from it, right? and it's calibrated for specific workloads, which to us means that it's not very useful, like for a generic classification, because we don't run those workloads where it is calibrated, and then because what we would like to have would be to be able to distinguish, like, say, VNNI instructions from ADX instructions from something else, which is not what this thing is doing. So,
right, but with the general idea of giving architecture the possibility to classify a task and use this classification to index different power curves.
Right.
The general idea might help with this particular issue.
Yeah.
Whether or not the Intel classification thing that Ricardo posted will actually work as we want it to is a different.
Right.
But those tables, they were named after those instructions. Were they just like the numbers were wrong, or the whole scheme?
I think so. So basically, just the one that we had in, I'm not sure about the current generations of CPUs, but the one we had a while ago was basically able to distinguish T-pose loops from something else, and that's it, right? Effectively, because so, but yeah, the idea is kind of sound, but it needs to be, implemented in hardware and firmware actually to match our assumptions, which.
There was also another limitation. It was only about kernel task and no user space task.
No. So there are a few. So the way you carry out the classification also matters, because if you only measure a tiny fraction of your CPU time, right, and you happen to measure the time spent in the kernel, you always deal with integer instructions. So this is another thing but this is an implementation detail, quite important, like how to do it in the CPU.
Cool. Yeah, I think there are ideas on how this could be done. I haven't really done it yet. The next thing is.
So I have one more comment on the classification thing. So we can, in theory, put that classification in the kernel, like measure everything, create a table and put it there, and it doesn't need to be done in the hardware. But then we would need to do it for every single SoC, right? And then this is a bit.
That's a little.
Yeah.
But I mean, we can allow architectures to fill it in as needed. So if somebody wants to go through the effort of doing
right, so
and classifications, then they can.
Yeah.
Yeah, I think it would make sense to let it be an architecture thing, how those classes, well, both how the classification gets done, but also how many curves and how you come up with them.
Yeah, it just indexes into the power model.
Yeah, that would make sense. Cool. How far are we on time? Wow, time flies. Then I looked at Android, because being ARM, we care about mobile, and we're trying to do experiments on mobile devices, and we're realizing that actually the devices that are shipping, there is something called Android mainline kernel, which I think is where all vendors start. But then Google has added this thing called vendor hooks, which is basically a cold site. That's those cold sites scattered across the kernel, where you can kind of from a module attach something to a callback, and you can actually pretty much override the scheduler that way. I just did a quick grep through fair.c and found that there are actually 35 cold sites in there, so you can see it's quite quite pervasive. And those modules using those call signs are sometimes really hard to find. So we actually do not know exactly what vendors are doing. But I think my point here is that it seems that also here there are areas where the mainline solution might fall short of what partners need to, or vendors need to ship a product.
But if we can't even find the source code for the standard rules, then and they're not talking to us, then we can't help them.
We can't help them, but is that because they have given up on us, or we haven't given them enough room to actually go and make a kernel that's closer to mainline do what they need?
It's also that not everybody uses the same amount of vendor, so you have thousands of, not thousands, but multiple
So this,
and follow all of them it's not possible.
Yeah, so this might also look worse than it is, because 5 of them might be used by one vendor and 5 different ones might be used by another. But the point is that there are many places where they apparently hook in and override what we have in mainline. And there must be a reason why they do it, otherwise they wouldn't spend the engineering time to go out.
Yeah, those reasons might be because they have old test scenarios and the test shouldn't fail, and that's why we don't really know. I mean, how severe this is, why they do it. If they have their own
we don't know. So this was.
Supposedly, someone could demand the source code as a full GPO license.
Yes. But who should that be? I mean.
It have to be distributed. As long as it's on one of the devices, isn't that distributed? So you have to buy the device. Someone must have bought the device. Well, you have to find someone want the device, so you have to find them to get you.
But the thing is even more complicated because they have multiple changes, and those changes they interact with each other. So you only have the chance to run it on the device itself. And if you want to understand it, it's huge.
Yeah, that's often impossible because it's not just one module hooking into one.
Find somebody knowing where they still have it.
We've seen that they hook into various places and they created whole backbone network between drivers and everything that just coordinates across multiple modules. So if you kind of want to take one out and study it, the whole thing falls apart. It's either use everything or nothing. So it's really, really hard to work with. I'm not sure how to untangle that mess. I think that's for the vendors to do. But if we don't sort of give them a way out of that mess, then it's only going to get worse, isn't it? I'm not sure where Google is in all this, but it should be in their interest too, I think, to try to sort some of this out. So anyway, another thing which is making it difficult to use the mainline scheduler as it is that Unreal, and that's probably also the reason why we have all those vendor hooks in Android, is that for every piece of hardware that comes out, there are always some implementation constraints. And they change from generation to generation, and it's really hard to come up with a generic solution which is future-proof, who can handle all these things. I mean, just a simple thing that we observed on the Pixel 6, which is a relatively old device now, is that because you can't have as many voltage and frequency domains as you would like, they had to cut trade-off, and that was that the level 3 cache, which is shared amongst all CPUs, is in the same clock domain as the little CPUs. And that meant that you have this constraint that you need to increase the frequency of the level 3 if one of the big cores goes really fast, otherwise you have a terribly slow memory system. So there they introduced this back channel to have a lookup table where they say, okay, if the big core goes this fast, then we need to bump up the little core because then the level 3 cache performance comes up with it. And those dependencies, how would we capture those in the kernel?
It's doable now with the latest energy model and the link and the notification that you bump up somewhere.
The thing with all the notifications and callbacks is that it always takes time. And some of these things are just super aggressive. I mean, they might want to change frequency at sort of microsecond granularity, so we can't really do it.
I have seen all this. There was some change in the mainline scheduler around the notification from the SCMI, but also the CPU frag to say that I have dumped up your frequency.
Yeah.
And I saw that one of the goals was for this kind of a hardware dependency between the cache and the...
Yeah.
This doesn't run SCMI, for example. So,
Sorry?
So this platform, for example, doesn't run SCMI, so do many. It's a nice solution for SCMI. Although it's still not really under schedule control, then it's just you're aware of the fact that frequency was raised, yes. Which is better than nothing for sure.
Yeah, so this is an old example of why I think vendors go and do custom hacks. And then we get to what I've been working with Christian on is kind of a related problem. So on our most or upcoming systems, we have an architecture extension called SME, and it's really some extra instructions that can do matrix operations. And the problem there is that the hardware to actually implement those instructions is rather big, as in many transistors. So we can't afford to put one inside each core. So we have one or more units that can be shared. The architecture allows that. And that leads us into some really interesting scheduling problems, because it means that for particular workloads that uses these instructions, the throughput is actually not decided by the CPU core itself. It does fetch the instructions and issue them, but they actually get retired in a shared unit. And that shared unit might be in a different clock domain than you, and it can be shared with other cores. So that means that if you have something that's using this shared unit, first of all, you don't want too many sharing it. But even if you don't have contention problems, then the most efficient use of that core depends on, well, there's no point in actually having a big core driving it, because the throughput of that unit can be saturated by a medium core, we expect in most implementations. Which means that if you have tasks that you do use SME, you actually want to affinitize them to a subset of CPUs. And it has to be pretty quick, because the bursts where you do use SME are relatively short. So we can't just do something we sample on the tick or something like that, where we detect if a task uses SME. We have to be pretty aggressive there. Otherwise, we miss the window of opportunity. But I've experimented with this and found some tweaks that do show some potential. It's still early days because we don't have access to hardware yet. But that suggests that there is a win if we can steer where those tasks do run. But we can't see a way to actually make this work upstream. We've prototyped it. Well, when I say we, I mean Christian. Prototype this using Android vendor hooks, where this was really easy to do because we have hooks everywhere. So we can just go in and override the affinity mask and add an extra one, a bit like it was done by Will for the AR32 problem.
How do you know whether or not the SME instructions are to be used? Can you have to trap or?
We have a trap because of the extra context. We don't want to carry that around unless a task is actually using SME, but that's kind of a once-in-a-lifetime flip. I mean, the first time you access SME, you trap, you set the flag, and then you have that context forever. We actually don't use that. We use some hardware counters to tell us how much we use the SME, and if we did, we go and update the CPU mask.
But just to piggyback on this, we can't just use like a one trap, because if our solution is to schedule on a smaller core, not like AVX, the classifier thing, you would actually be heavily punished by a wrong classification, because if it turned out to be just a sporadic SME task or whatever, that we just ran a non-SME task on a smaller core, racing through this.
So what I was thinking about was the MIPS code. MIPS has some rather creative hacks that you might not have seen.
they at some point had units with FPUs on every other core.
Yeah.
And if you issue an FU instruction on a core that doesn't have it, it traps. And then it migrates tasks to a core that does have it. And
Wonderful.
Execution. This code is upstream, it's vile, but it's there.
So you're suggesting we
I'm not suggesting it.
good.
But yeah, this is it exists.
Yeah.
I think it's safe to just not be as drastic because technically it runs everywhere, right? Like we don't really want to trap. We don't absolutely have to.
So this thing it wouldn't actually run because 3 did not.
Yeah. And then there's no choice but to do an expected trap.
But then, if you're able to detect that with your hardware monitor, we are about to be able to classify the task.
Yeah, we would.
So
We
we're
would.
about to decide PCC, at least at the web, being able to classify the task using the PMU. As well, so okay, more SME, or
Yeah.
then you can make some decision according to the possible throughput or the compute capacity that you have.
Yeah.
You can probably also impact.
But again, then you need to pull in a lot of hardware-specific stuff because how many CPUs do you have sharing this unit, and how is it shared? Because that's left open to the implementation.
But I
So
mean, from the task point of view, being able to detect if a task, which kind of instruction a task is using, that's what you need first, even before being able to know how is your hardware topology.
yes, so we would need what we talked about in the beginning. We need some way of the hardware to tell us what kind of task this is. Whether you do it using counters in architecture code, or if it's offloaded to hardware or microcontroller. But even if we do have that classification, I'm not sure if we can extend the energy model concept far enough that it will give us what we want in all scenarios, because sometimes I think some of these policies are like, we always want to run it there. We don't want it to be sort of a factor in a much bigger equation where it might or might not make a difference in the end. It doesn't leave the vendors very much freedom to override things unless we come up with something with 1 million scheduler tunables, which we have been against in the past. So I'm not sure what the right solution is. The slide was just to illustrate the problem here, that if you imagine that your throughput of your yellow bit here, that's the same almost independent of what CPU you're using. On the little CPUs you can't saturate, or we don't expect you can saturate the shared unit, and that leads to another set of interesting problems. But yeah.
It looks like from this slide, it looks like this workload at least is better off on the big CPU, right? Even though it's using SME. It looks
Yeah, so this is just made up.
yeah, but it also illustrates the point that it depends on how often you do it. Like,
It does. And the other thing is, because of the potential contention issue, that if you end up using SME from every single CPU in the system, then you are most likely ending up contending on access to the shared unit. And because the speed up varies, how much gain you get performance-wise of using the SME unit, for some workloads it doesn't make sense to use it from all CPUs. So if you want to compute as fast as possible, you probably want to split your workload in a way where some CPUs use SME to accelerate the work, and others use regular vector instructions. And if you do it that way, what you will probably see, or what we expect to see, is that the uplift of using SME on the big core is not very big, because it has very high-performing vector implementations. So therefore, the performance gain you get from going from vector to matrix is small, whereas if you run it on the medium CPU, you see a much bigger increase because their vector implementation is weaker because of efficiency. So therefore, if you do have a scenario where you have a system where you have load on all the CPUs, what we really want to see is that those that use SME actually end up on the medium ones, because first of all, they're better matched to the throughput of the shared unit, but we also want it because that actually gives us the best overall throughput. Because if somebody is going to use vector, because we can't contend for SME, all of us, then those vector tasks should preferably be running on the big CPU because it has a very efficient or high-performing vector implementation.
Yeah, that makes sense.
So there are all these trade-offs and scenarios to think about, and that's why I'm thinking, yeah, how do we express this in a generic way? And this is just one problem. And on the previous slides, I just kind of had them to show that there are probably lots of problems like that out there, and that's why we have all these vendor hooks in Android, I think. So, what's the way forward?
I guess it's really a shame that we cannot kind of reuse that, I guess, knowledge that vendors might have, because maybe everybody has kind of find a partial solution to these different ways, and
I think so, yes.
And we have to rethink from scratch. But it would be nice if we at least there might be good things.
I think there are. I would be surprised if not all vendors have a way of doing thermal leveling where you rotate tasks between the big CPUs because they heat up very quickly. And we don't have that in upstream, but I think all vendors might have it using those vendor hooks.
Also, we might not have access to all the extra hardware, right? So
it's hard to get access to the hardware, and it's hard to find a kernel you can build and actually run where you can actually experiment with these things.
It's another thing, like if you have everything in-house, right? Even if your solution is not 100% sober or clean, it's still good for a product because you control the environment.
Yeah.
If you have it like an open source code and people use it or use it differently, then all kinds of problems can occur. That's why it's much harder to extract the upstream bits out of something that's complicated with this stuff.
Yeah.
And I think this takes time and energy, and people are not always willing to spend.
And who should do it if there is not much incentive for phone vendors to upstream their work? How do we fix this? I mean, my selfish interest in this is because we have SME and we want to optimize for it. And yes, we can go off and do it using vendor hooks, but that will only serve the Android segment. SME is for everything. So what do we do for systems that do not have vendor hooks available? So going with supporting classifications and different energy models, I think will go some way, but is it enough? Is it a good idea that we're trying to push everything into generic code using some abstractions? Where do we need to draw the line? Do we need something which can more aggressively override what the scheduler does? I mean, for my example, I'm being selfish, I could probably get most of the way with what we need for SME, but just having sort of an extra CPU mask that the scheduler would observe, either apply directly on top of the normal affinity mask, or be a mask that we sort of look at when we look for a potential CPU for a task and say, okay, architecture says that this subset of CPUs is preferred, so I'll try to pick one of those if one of those are available. John?
I'm curious how much you think like this architecture persists. Because I feel like there's a lot of times where as people are kind of experimenting with these ideas,
yeah,
you kind of float where it's like, okay, well, we'll have one SME for this share, and then at some point it's like, well, you gotta have them for all of course, like the FPU idea for, it's like that's kind of rare.
Yeah.
And so, trying to design things for architectural quirks that aren't going to maybe endure seems like...
I don't think they will endure, but there's going to be a new one for the next generation.
Yeah, and I mean, in a way, definitely have their troubles, but they also provide kind of space for
exactly
often hardware problems, right? Like, there may be an issue with the SoC design.
Yeah.
And they give ways to kind of put in workarounds that don't necessarily.
I agree.
So I don't know. That's one of those things where sometimes this is kind of a nice little escape valve that people are able to do their ugly things for this kind of short-term period. But for longer-term architectural designs, that's actually what we need to be discussing for being street.
Yeah, I'm just thinking that right now it seems we kind of have a scale from upstream to vendor hooks, and right now upstream is perhaps too conservative for multiple segments. It's just not just Android. I mean, we have talks from people interested in data centers and other things talking about. Steve, you're going to talk about scheduler governors. So it's kind of both ends of the spectrum who has the opinion that maybe what we have in upstream is not sufficient for real systems or real products. So who's actually left that just use the mainline scheduler today? If everybody's overriding it, why do we bother actually putting that much into upstream?
Don't spoil my tongue.
I just want to say, let's say I implement this, I get preferred CPUs mask. It's oversimplifying it a little because you mentioned the contention case, and that's changing over time, even if the task P has not changed in behavior.
Yeah.
So in my specific code, I would have to consider, if I return a different CPU, pref CPUs now, then a migration will happen. Is that worth it? Or do I return the same CPU mask as I've done the last tick or so, which would really be, on the order of hundreds of lines of code, like very scheduler specific, SOC specific knowledge living there.
Yeah.
And I question that, the community would be okay with that. I mean, maybe that's wrong. I don't even know if I'd be comfortable with that. But that's just what that would mean.
Yeah. I'm not saying that this would solve all the world's problems. I'm just that this could be one callback of maybe several to go a little bit towards what we have in the Android vendor hooks, but not all the way.
Just one point. So for this, you're focusing the ES behavior or any kind of SMP behavior? Because all this energy model and per CPU capacity.
That's only for ES, yeah.
Really about ES.
Yeah, where we could use architecture callbacks we can use for any system. SME is not just for mobile. In theory, it's for everything. Now, the implementation might look different if you put SME in the server implementation. So there, the problem might not be as bad as it is for mobile. Yuri?
Do you expect maybe a move from moves to Auspice CADX now that the thing is upstream from vendors?
I don't know. I don't talk that much directly to the vendors, but maybe some of the Google folks would have insight into where they are on SCAD-EXT. Because having both SCAD-EXT and the vendor hooks, that seems a little bit redundant.
Yeah, but with SCAD-EXT, you can't just partially override the SCAD. You have to rewrite further.
Yeah. Yeah, with the vendor hooks, it allows you to go in and, I don't like this function, I can just replace that one and have all the rest. Where with SCAD-EXT, it's all or nothing, isn't it?
For now. The other aspects of vendors can be all over the kernel. And that aspect of those back channels where you're talking with, the locking subsystem.
Yeah. Yeah, the vendor hooks allows you to almost have like an over kernel or something that just sits from above and control what we have in mainline. Any more comments? This is my last slide, I think. What I think we gathered is that,
More questions.
Yeah.
So how does it work when you compile a program that is actually using these assembly instructions? You know it up front from the kernel, so when you load the program,
You have that information in task structure or not?
No, because there is also the scenario where you call a dynamically linked library that uses asymmetry. Yeah.
So you don't really know what you have from?
No.
You know why it's running, that it's using SME, so it's...
You try on the first call.
Yeah.
To establish the context and everything. So you do get trust on the very first.
Oh, you get a trap on the first slide.
Yeah.
Why do you get a trap?
Just to set up the context and everything, because you always do that for every class. 99.9% won't be using.
It's not strictly necessary. It's an optimization because the context of, instead of just the normal registers and vectors, now you also have a matrix context, which is rather big, and you need to context switch that every time you switch between tasks. Yeah, so you don't want to allocate that and context switch that between tasks that do not use SMEs. That's why we try.
How do you call the instruction set? The CC is an asynchronous instruction, so it keeps doing other stuff while the SME instruction is running, or does it stop waiting for the
It blocks on, yeah. So that is why if you use it on a big CPU and you look at how often the backend stalls, then if you go really fast on a big CPU, you will see more backend stalls because it's waiting for the shared unit to.
It only stalls for like a cycle or two, so you can't like schedule it out and do different stuff. Like it's not that so.
It's
no.
Yeah.
Thank you.
Cool. Yeah.
You said that there are modified Android bedrooms. Do you have any idea how those are and what the vendors try to configure or what the manual is doing?
So, if I understand correctly, you're asking if I know what the vendor hooks are used for? I have ideas, but I don't know because I haven't seen the source code. Some of the source code I think you might be able to find out there somewhere, but obviously vendors are not really advertising those because it's their value add, isn't it? So they would always be reluctant to reveal what they're using it for.
But the trace point, the vendor books are kind of the standard baked into the Android kernel, right?
It's in the Android mainline kernel, if I'm correct. Sorry? All the Android kernels, but I don't know, where does it get added? Is that in Android mainline and then it goes out to everything from there?
Android mainline kind of has the intention to be as few vendors as possible, and so when they branch for the production kernels, vendors tend to add in what they get as they move forward into that. So it tends to be more on the product side.
So what you're saying is that the 35 I found is actually a small number.
Yeah. For 612, which is still pretty early in its productization period, I think there's 100 in scale. So not just fair, but so that's probably going to grow over the next couple of years.
So you could actually runtime patch the scheduler away almost, just in it function by function. Yeah.
Is it because of UDF or all sorts of things? I think they want to change
Wow. Okay. Well, my takeaway here is that there is some appetite on the task classification idea, but I don't hear any great ideas coming up for how to accommodate all these tweaks just yet. So that needs more work, I think.
So I haven't looked in detail, but for the ARM64 CPU that can't run ARM32 instruction, there is already something like a specific CPU mask available.
Will's horrible hack, yes.
Yeah, where you say, okay, I can't run on this. To be honest, I never look at the detail and how it was working. But is it? Can it be something
it's a little bit worse than here, because there you actually have something similar to the MIPS problem that Peter just mentioned before, where you literally cannot run those ARH32 instructions on some CPUs. Yeah. This is not that bad. This is just for efficiency and performance.
In this case, this preferred CPU can be this CPU mask saying, okay, now I can't run on this CPU.
Yeah, but as Christian said before, it's not really a static thing. It depends on how the task behaves if we want to have this mask applied or not. Whether CPU can run AR32 or not, that's like a static situation.
There was once this idea of a soft CPU affinity, but I'm not sure.
Yeah, this is kind of what
the use case though. I don't know how frequently these things change.
I think that was discussed in the context of Android as well, where instead of those very hard CPU masks we had for the various C groups we had on Android, you could sort of let them be a little bit softer, so it would be kind of a preferred mask, whereas if the scheduler thinks this is a terrible idea, it could actually override it, where affinity masks today, they are set in stone. Unless the CPU mask is empty, would never override the affinity mask. So, okay. Thank you all for listening, and I'm looking forward to hear what others are going to say on related topics today. Thanks.